All right, the second part of our notes deals with inverse trig functions. And so what I want to do before we dive into the calculus of it all is just do a little recall of what an inverse trig function is. So just as a reminder from last year, we write this in two different ways, and it's pretty interchangeable within both textbooks, on the AP exam, depending on the teacher that you have next year for calculus. They may habitually say arc sine, or they may say inverse sine, or the same with all of our other trig functions. So just as a reminder, they mean the exact same thing, just different ways of denoting the same thing. So when we're dealing with inverse functions, again, our domain and our range are switching. And so what we used to input is now our output. So what we're getting out now are thetas, our degrees or radians, and in calculus we deal with radians, so we're getting out those radians, and what we're putting in is that ratio of side lengths. And so my domain we have to restrict, because if you remember, your sine function looks like this. And so if I invert this function, and I'm sure you remember this from pre-calc last year, it ends up kind of like snaking up and snaking down our y-axis, and that is certainly not a function, right? This does not pass. This would not pass the vertical line test. We'd have an issue. And so we have to restrict this function. And so for both sine and tangent, we can't restrict it within that first two quadrants, because if we do that, we still don't have an invertible function. And so what we do instead is we look for a part of the function that's either always increasing or always decreasing, and that portion that we choose is between negative pi over 2 and pi over 2. And so I like to kind of visualize it from this unit circle. I'm restricting it between negative pi over 2 and pi over 2. So my range of values that I'm going to get out from arc sine are always going to live between negative pi over 2 and pi over 2. And you'll see that when you put things into a calculator, you get the same thing. And then my domain is what my range would have been, right, for my sine function. So that's between negative 1 and 1. So if we're trying to put a value into sine or into inverse sine or arc sine that's outside of this domain, it doesn't exist. It's undefined. Cosine has the same exact domain, but what's really nice about cosine is that cosine starts here. All right, so cosine's pretty sweet in this case because it's always decreasing between 0 and pi. So I don't have to go into that fourth quadrant and deal with negative pi over 2. I can just go from 0 to pi, which is really nice. So my range here is going to be from 0 to pi inclusive. All right, and then lastly we have tangent. Tangent's going to follow very similarly to sine. It's going to live between pi over 2 and negative pi over 2, but we know that cosine is in my denominator, and cosine is 0 at both negative pi over 2 and pi over 2. So we can't get those values out because there's tangent lines, vertical tangent lines there. So we have not included, right? So we're using parentheses because negative pi over 2 and pi over 2 aren't included. And my domain for tangent is all real numbers because tangent we can get out all real numbers. All right, so let's just do a quick refresher. If I'm looking for arc sine of negative root 3 over 2, that means I'm looking for what theta will give me negative root 3 over 2, and it has to live between these two quadrants. So I know it's going to be a negative value because it is going to be in my fourth quadrant, and sine is negative there. And then the way that I think it through, for my students that had Mr. Littlefield last year, you guys are making that triangle to figure out what that value is. The way that I think it through is I say, all right, it's root 3 over 2. Sine is my y value. So it's going to be my taller of the two triangles. My taller of the two triangles has the larger angle. And so it's going to be negative pi over 3. All right, secant, inverse secant of root 2 is going to be where cosine equals root 2 over 2, which is pi over 4. It's positive, and so I know it's just pi over 4. Any negative values are going to be in that second quadrant. So if it was a negative root 2, then we would have had 3 pi over 4. Because as a reminder, all students take calc, cosine is negative in this quadrant. All right, and then where tangent equals 1 also at pi over 4. So that's the same value. All right, so let's go ahead and try some of these. We're finding the derivative. Oh, we can't yet. So what I need you to do is go ahead to your bookmark page. I'm going to do the same. I'm actually going to bookmark this page as well so I know to come back to it. So we're going right here. So we have everything filled out now, and now I need you to make a section called inverse trig functions, and that's what we're going to look at today. I'm going to talk you through these so you have an idea of kind of what's going on, but I would just pause the video. You're going to need to leave a little bit of room. So I would like skip a line in between each of them because each of these is going to be a fraction. And so you can't really fit that all in one like college ruled line. All right, so I've set them up in this way very intentionally because it's kind of how I memorize them so that I know what's going on. So first of all, remember that all of the cos, so everything that started with a C in the last one, the cosine, cosecant, cotangent, those all were negative when I'm dealing with the derivatives of my trig functions. The same thing's going to relate here. I'm intentionally doing a ddx. Oh, I don't have my highlighter. But I'm intentionally doing a derivative with respect to x of u because these generally exist with the chain rule. So I want to just kind of jump right to that. And then the thing that I'm remembering is sine starts with an S. I'm subtracting. So the derivative's going to be, and I'll go through this proof next class. I just don't want to overcomplicate things on a video. Is going to be u prime all divided by 1 subtract u squared, the square root of 1 subtract u squared. So the derivative of u all over the square root of 1 subtract u squared. So if this is sine, cosine is going to be the exact same thing, just negative. All right, for secant, and again, pause the video to write it down. For secant, it's going to be the same thing. Now I'm just switching the 1 and the u squared. So it's u prime all over. We're going to have the absolute value of u in front, the square root of u squared minus 1. So we have that absolute value in front, and then we have the square root of u squared subtract 1. Cosecant's going to be the exact same thing, just negative. And now tangent's my favorite, u prime over 1 plus u squared. So tangent together, we're adding instead of subtracting. And cotangent's going to be the same thing, but negative. So there's really only 3 to memorize because the other ones are just negated, which is nice. And what I'll do real quick is just go through this proof so that you can kind of see where it's coming from. So if we want to have the derivative with respect to x of inverse sine of x, actually, let me set that up a little differently. And you don't need to write this down. I just kind of showed the students in the other class this. We ran out of time to have them discover it on their own. We're going to leverage the same type of thing that we did with e to the x, or rather for natural log of x. We're going to use the inverse function to help us find the derivative of this inverse function. So the inverse of sine is just sine. So I'm going to rewrite this as sine of y equals x. And so the derivative with respect to x of sine of y is cosine of y times dy dx equals the derivative of x with respect to x is 1. I get dy dx by itself, and I get 1 over cosine y. Well, that doesn't help me yet because I don't have anything up here in terms of cosine. So I'm going to rearrange things a little bit, and I know that I can rewrite cosine y using my Pythagorean identity. So I'm going to go ahead and write that over here. I know sine squared y plus cosine squared y equals 1. Cosine squared y equals 1 subtract sine squared y. Take the square root of both sides. Cosine y equals plus or minus the square root of 1 subtract sine squared y. Well, we're going to force this one to be positive because it's going to work out whether it's negative or positive, and we're just going to force it to be positive for this. So we have dy dx equals 1 over the square root of 1 subtract sine squared y. Now we do know that sine of y is equal to x. So we have dy dx equals 1 over the square root of 1 subtract x squared. So if we were not using the chain rule whatsoever, this is our rule. However, if we're using our chain rule, right, we would then multiply this by the derivative of that inside function with respect to x, which is where that u prime and u squared are coming into play. All right, so let's go ahead and take a look at some of these examples. So we're taking the derivative with respect to x of arc sine of 2x. So my u is 2x, which means u prime is 2. So I have that all set. My derivative is u prime over the square root of 1 subtract u squared. Now I'm just going to place things where they go. And I'm done. Let's try another one. I end up with 2, all divided by the square root of 1 subtract 4x squared. All right, for this next one, we're going to do the same thing. I know that u equals 3x, which means u prime equals 3. I have u prime all over 1 plus u squared. So 3 over 1 plus 3x all squared, or 3 divided by 1 plus 9x squared. For our next one, we have a which means it's going to be negative. So we have negative u prime all over the square root of 1 subtract u squared. My u is x to the 1/2, or square root of x. So my u prime is going to be 1 over 2 root x. So I have a negative 1 over 2 root x, all divided by the square root of 1 subtract the square root of x, all squared. Now I'm just simplifying. So I'm going to go ahead and multiply by 2 root x in the numerator and the denominator. I get negative 1 over 2 root x times the square root of 1 subtract x, which I can then simplify. I could leave like this, or I could rewrite as negative 1 all over 2 square root x minus x squared. Honestly, either of them is fine. And again, either could be written on a multiple choice question. Last one is secant. Secant is going to be positive, so we have u prime all over. This one has the absolute value of x, and now we switch the order. So, I'm sorry, absolute value of u. Boop. So we have u squared subtract 1. So still subtraction, because it's not together like tangent and cotangent. Where it has that my addition, but we do switch that order. And so my u is x cubed, and my u prime is 3x squared. So I have 3x squared all over absolute value of x cubed square root of x cubed squared subtract 1. So we get 3x squared all over absolute value of x cubed square root of x to the 6 subtract 1. Now, this x cubed is being forced to be positive because it's surrounded by absolute value. If I were to go ahead and take a look at the absolute value of x squared times the absolute value of x, that's the same as the absolute value of x cubed. This guy right here is always going to be positive anyway, right? Because anything that's being squared is positive. So I can actually take that out. So I'm going to take that out and say this is 3x squared over x squared times the absolute value of x times the square root of x to the 6 subtract 1. And now what I can do is cancel out those x squareds. So I end up with 3 over the absolute value of x times the square root of x to the 6 subtract 1. And I'm good to go. I guess I'm in a cloud mood today. All right, so work on that problem set for homework tonight. You'll probably have some time in class to work on it as well. I've also posted a Delta Math Unit 2 review that's completely optional, and by that I mean if there's areas that you're struggling with, and this could be one of them, you could go and watch some of those videos to get another different explanation, or try some of those where it gives you feedback on what you're doing right and what you're doing wrong and gives you like examples of how to work through them. So that's another strategy that you could use. And I will see you guys next class.